Information conveyed by data. Suppose the data we receive does not resolve all of the uncertainty of a situation. For example, earlier when we received the data that a randomly chosen card was a heart, some uncertainty was resolved, since we now know more about the card than we did before receiving the data. Yet, we still do not know the exact card, which means some uncertainty remains. In light of this, we can modify equation 1 from earlier as follows. Capital I of data is equal to log base 2 of 1 over p sub data. In our example, the probability that the randomly chosen card is a heart is 13 out of 52, which is equal to 0.25, which is the number of hearts divided by the total number of cards. Therefore, the information content of this received data is log base 2 of 1 divided by 0.25, which is equal to 2 bits. This example is one we encounter often. We receive some data about equally likely choices that narrow the number of remaining possibilities. The information content of such data can be calculated using equation 2. More formally, suppose we are faced with n equally probable choices, outcomes, and are provided with data that narrows the possibilities down to m choices. Since the n choices are equally likely, each has probability 1 divided by n, which implies that the probability associated with the m choices is m times 1 over n. Consequently, the amount of information received based on the above data is the following. Log base 2 of n divided by m bits. Example 1. Applying equation 4 to the previous example, setting n equal to 52 and m equal to 13, yields the following. Log base 2 of 52 over 13, which is equal to 2 bits. This means we have received 2 bits of information when learning that the randomly chosen card is a heart from the deck of 52 cards. Hence, the information content of the received data is 2 bits. Example 2. Referring to example 1, suppose by some means or another, we know that the suit of the randomly chosen card is in fact a heart. Compute the information content for data that provides us with the exact identity of the chosen card. Since we already know the suit of the card, there are 13 possible values, ace through king. Suppose the data informs you that the chosen card is the ace of hearts. To compute the information content of this data, we use n set equal to 13 and m set equal to 1, yielding log base 2 of 13 over 1, which is approximately equal to 3.7 bits. Example 3. Observe that if we had, from the very start, received data that the randomly chosen card was the ace of hearts, then the information content of this data would be log base 2 of 52 divided by 1, which is equal to 5.7 bits. We can summarize the calculations of the information content for examples 1, 2, and 3 in the following diagram. As the reader may have anticipated, the information content of 5.7 bits is simply the sum of the information content of the 2 intervening steps, which produce 2 bits and 3.7 bits respectively. A mathematically more aesthetic depiction is as follows. Technical reminder, the additive properties of the information content of independent events will likely not be a surprise. It is based on 2 fundamental properties. 1. The probability of 2 or more independent events occurring is the product of the probabilities. And 2. The logarithm of a product is the sum of the logarithms. Example 4. For our final example, we provide numerical answers for the amount of information conveyed by data in Table 1 from the previous section. Compare these to your answers from earlier. Summary. The more uncertainty that is resolved by the data, the more information we have received. For instance, learning that the original chosen random card is the 10 of diamonds resolves all of the uncertainty regarding its identity. Hence, it has the highest information content of the data listed in the table. Whereas, learning that the card is not the ace of spades resolves very little uncertainty regarding the identity of the card. Hence, it has a very low information content. In the next video in this series, we will look at the concept of information entropy.